Hello everyone, this is Professor Iris Miano giving you your Week 3, Day 6 lecture video on sections 3.2 and 3.3, informal geometry and measurement and early definitions and postulates. So there's a lot of information that's going to be coming at you in this video to give you a firm foundation in regard to lots of terminology and notation. So here we go. Let's just jump right in. And if you've printed out your lecture notes PDF document, this is going to be a great way for you to organize all of the little drawings that I have in play to help you define all of these terms. There's a little space provided next to each term. So definitely draw yourself some pretty pictures to get to know all of these terms. Okay, let's start with a point. Now, as you can see, I have it lit up in red on the screen here, and I have 3 points as an example, and they are labeled with uppercase letters A, B, and C. Points are defined as locations without size in a particular plane or on a line. And what else do I want to say about points? Yeah, they have also no dimension to them. Not that that's something you need to be terribly concerned about. What we really want to know, or have you know, is how points are labeled. They are always labeled with uppercase letters, as you can see in the examples here. A, B, and C are fine identifiers for those 3 points, and the names are always just kind of right next to the dot representation for the point. Okay, moving on to a line. A line is a straight trajectory that goes off an infinitely long manner in either direction in which it is pointing. So lines do not have any particular length. They have infinite length, I guess you could argue. And there's a couple of different ways that you could label your lines. You can label them with lowercase letters, as you can see here on the screen with the letter M. This would be line M. This here, with the incorporation of 2 points A and B on the line, give another way that you can name the line. Using this notation with this line on top, it's kind of like acting as a hat with the identifying points A and B. So this symbol right here would would be read as line AB. Now, if you have a straight trajectory with endpoints on them, you're talking about a line segment. And so line segments, by definition, have length to them. You can measure them. That's something that we'll actually talk about in this section. And the naming of them has to do with the points that act as the endpoints for the line segment, and their notation changes when you compare it to the line, in that the hat doesn't have arrows on either end. So no arrows on either end, you're talking line segment. If you go back one, if we have arrows on either end for the hat, we're talking about a line. Okay. Points are said to be collinear if they can be represented as lying on a single line. So for instance, in the visual that you see here, points A, X, and B are collinear because they happen to lie on line M. Now, do collinear points have to be on a line in order to be labeled as collinear? No. By definition, they only have to be able to lie on the same line. They have to be in line with one another, but not necessarily on a line. A ray is kind of like if a line and a line segment had a baby, because it's a line segment on one end. There's always one endpoint. In this particular figure, it's point A, and then there's always another point B that has to be on the ray in order to give the ray some kind of direction. So the endpoint is kind of, the end of it. Not saying anything spectacular, LOL. But then B is telling you, in which direction it's more or less pointing. And so it goes on forever and ever and ever in the B direction. But yeah, so in this regard, since one of the ends of the ray go on forever, then technically no ray can have any particular length. They have an infinite length, but they do have a starting point, and it's always going to be the one blunt edge of your ray. And the notation associated with naming a ray is a hat that's a straight line trajectory with only one arrow point, and the arrow point is pointing in the direction in which the trajectory is traveling for the ray itself. So this would be ray AB. You would not call this particular ray ray BA. That would be inappropriate, because then that would indicate that A is on the ray itself in the direction that it's pointing, but that's not the case. A is the end point, so that's always going to be the first letter that's mentioned in the name of the ray. Now, when two rays are joined at their endpoints, then an angle is formed. Okay, so here's an example of an angle, and you'll notice that there are several points involved in the angle, and so they can be involved in naming the angle. I'll have all the angle name possibilities listed in just a second. Also, in an angle, a couple of things to note is that you don't necessarily have to have the meeting of the two rays be explicitly shown as a dot, but there is a point there and it has a name, but the dot may or may not be there, is what I'm saying, like in your textbook and other places where you read about geometry. Furthermore, the interior of an angle could have within it a number, and that is another way that you could name this particular angle. In fact, these are all 4 different possible names associated with this angle here. You can ride the edge of the angle in such a way that you name the letters in order from the start, or the starting edge of the ray here, C, go through A and then end up at B. That's angle CAB that you see here. Also, an equivalent way of naming this angle would be angle BAC. You could also go in the other direction, but you cannot start at the vertex in order to name an angle. That wouldn't make any sense. So, for instance, this angle cannot be named something like angle ACB, right? In that case, the vertex would be a C. I know I haven't defined vertex yet. That's the next term in line here, but yeah, the vertex is going to be, spoiler alert, the connection of the two rays that form the angle. Okay. Anyway, furthermore, if you have no other possible angles involved with the rays that you're using to form the angle, you can use the single letter name in order to name the angle. But that might not always be appropriate depending on what other elements are going on in the figure. I will point that out to you, what I mean by that, when the time comes. Furthermore, if there is a number inside the interior of your angle, you can use that to name the angle as well. Okay, like I said a second ago, the vertex is defined as the connection point between two rays that form an angle. Okay, there are 2 polygons that we're going to introduce at this time. We're going to go into much more depth on these polygons a little bit later on in the semester, but for now, here is a triangle. It is a 3-sided closed polygon figure. This triangle's name could be triangle ABC. That'd probably be the most intuitive, straightforward naming of this triangle. However, there is no wrong way to name a triangle. You can literally come up with any combination of the 3 letters in any order you want, and that is an okay name for the triangle. Now, when we get into talking about triangle congruency or similarity in a much later chapter, we will care about the order in which we are naming the points to name the triangle. It'll become relevant a little bit later on to be careful with that. Now, so that's all the ways that you can name a triangle. Rectangles are 4-sided closed polygon figures in which 2 opposite sides are have the same measure and are therefore congruent. I'll talk about those concepts a little bit later in this lecture. And so there are 2 pairs of those. But anyway, for our purposes, we just want to know how to name them. And here are all 8 possible names for this rectangle right here. So there is a rule associated with naming rectangles, and it is you have to go around the figure. You can't use a sequence of points or vertices for your rectangle that cross the interior. So for instance, if you look among all of these 8 possibilities here, there's not any appropriate name for this rectangle that goes rectangle A, C, B, D. You see what I mean? Because you would have to cross the interior of the rectangle. You have to go around it. So you could start at A and go in this direction. Could be named rectangle A, D, C, B. You could go from B and go in the opposite direction. This could be rectangle B, C, D, A, and so on and so forth. And these are all 8 possibilities. You don't have to think about it. I have them there for you, locked and loaded. Okay. Cool. So moving on, let's talk about measuring line segments. So as I said before, line segments have a particular unique distance measurement associated with them. And the way you generally measure line segments is by using some sort of measuring device, like a ruler. Now let's say we have this pretend, just on the screen. It looks like about probably a centimeter ruler, a partial one. Now, how would you go about measuring the line segment RS that we see here? Well, you would line up your measuring device accordingly, where the 0 or the cipher of your measuring device lines up with one of the endpoints, okay? And then you want to simply look at the approximate location of the other endpoint. So I would say that RS is, more or less, all physical measurements are approximations. We're just going by our naked eye the best that we can. And I would say that RS is 8.5 centimeters with some confidence. And now notice that I have 2 different notations here. This is not an error, okay? Now when we name the line segment, it's customary that we put the hat on top, okay? This is line segment RS. When we refer to RS in terms of its measure, it's appropriate to take the hat off. So this right here, this RS with no hat, technically the way you would describe this or read this right here would be the measure of line segment RS. Yes, all of that goes into just the simple R and S sitting next to each other because we want to read the context of this scenario here, where we've measured the line segment and we are reporting it. So therefore this reads, the measure of line segment RS is equal to 8.5 centimeters. Okay, great. Let's measure some more. Let's throw a point X into the mix on line segment RS in such a way that we create 2 conjoined line segments, RX and XS. So if we want to measure them, we would, starting with line segment RX, that is, start at R, go to X, and we can say, okay, it looks like the measure of line segment RX would be about 3.5 centimeters, right? Okay, and you would report that in the following way here using appropriate notation. Now, what would be the length of R segment XS? Well, you can use what we were stating earlier about the entire collective line segment RS, noting that it was 8.5 centimeters, subtracting off the distance for RX, and that can give you the distance of line segment XS, which is 5 centimeters here. Okay, cool. So using a simple little bit of subtraction will help you do some measurements sometimes when you are measuring collective conjoined pieces of a line segment like we have here. Moving on, let's say we threw X out and we put in a different point Y on line segment RS. So then if we wanted to measure the lengths of RY and YS, the measure of line segment RY looks like it would be about 4.25, if I'm saying that point Y looks like it's halfway between 4 and 4.5. So let's just say that that's the case. And if that's the case, then we can use subtraction again on the collective line segment measurement RS, which was 8.5, if you recall, and say, all right, if I subtract 4.25 from that, I'm left with 4.25 again. Now, what do you suppose is very special about point Y in terms of line segment RS? It is, in fact, the midpoint. because it has on either side of it the exact same distance in terms of the collective line segment RS in which it lies. Okay, and so since these RY and YS line segments have the same measure, we get to also say that they are congruent. So we're going to introduce this new piece of notation here, and it's an equal sign with a squiggle on top. And so the congruency designation is for named line segments or angles. We'll have instances in which we talk about angles being congruent as well. And it is a separate designation that we need to have distinct but related to equal measures, okay? In fact, we define congruency in terms of this concept explicitly. If two line segments are congruent, then they have equal measures. And the reverse is also true as well. We will see an explicit, re-examination of that very fact a little bit later in this lecture video. Okay, now measuring angles. Now I told you at the beginning of the semester when we went over the syllabus that you did not have to buy yourself a protractor to measure angles, and I meant it. However, I'm still going to teach you how to measure angles using a protractor. So you may notice on your lecture notes that there is this angle RST, or you can call it angle S, or you can call it angle TSR, right? According to the naming rules that we just learned. And there is a protractor resting on top of it, right? So this is what you see on your lecture notes. And so how would you use this protractor to measure angle S? Or the other two names that I said would be relevant. Well, notice that there are two different numbers, right? For, and this is a protractor, yes. Okay, in case they didn't make that abundantly clear. So notice at the, I would say the base of the angle, the ray that's like horizontal is often referred to as the base ray or whatever. It's lined up with either the 0 or the 180, depending on how you're reading this. Let this be measurement 0. So that means as far as the angle measurement of the placement of ray SR, that's going to be read with the top collection of numbers. So here is 30 degrees, and it looks like we're one tick away from that. So I would say that the measure of angle, if I'm going to call it angle RST, is 31 degrees. So notice this notation in front of the angle name. This lowercase m is mathematical shorthand for the measure of angle RST. All right? And it reads as 31 degrees according to this protractor reading. Another thing that I wanted to point out that I didn't mention is that when you are lining up your protractor, if you use a protractor to measure angles, that is, make sure that the vertex of your angle is in, this central, like usually there's a hole right here or some other kind of like measuring device, kind of a cipher there. Kind of like the zero edge of a ruler. It kind of has the same kind of vibe. Okay, anyway, moving on. Here are some more important terms that we're going to define. And I'm going to define these things in terms of kind of a lot of figures. So if you ever need to like pause to catch up on drawing the figures, if you want to draw your own on your lecture notes, like I recommend you keep the pause button handy on this one, because I might go through this relatively quickly. In order to bisect something, by definition, you would be cutting something in half, because you can break down this term in terms of its like root words, bi meaning to, sect meaning cut. And so if we're going to bisect a line segment, like let's say line segment XZ that we have here, we could do so with an additional point called Y in this case, as long as the measures on either side of Y getting to the endpoints are equal to each other, then we can say that it bisects. And so the line segments created with the incorporation of the bisecting point are equal in measure and therefore congruent. And the same is true with angles, but you need a ray in order to bisect an angle. So here we would say that ray DB, since it in its incorporation with the collective angle ADC creates equal measured angles, we would say that ray DB is bisecting angle ADC. So I have some ways that I could describe what's going on here that I think might be important to write down in terms of being able to define the term bisect. So there you go. And feel free to press pause right now if you want some extra time to write that down. Otherwise, let's move on to trisect. So if you understood what it meant to bisect, you're like, oh yeah, trisect, that means cut into 3 equal pieces, in which case I would say, yes, that is correct. So if you need to trisect a line segment, you must do so with 2 points, right? So to cut into 3 pieces, you need 2 points. To cut into 2 pieces, you need 1 point for a line segment. Similarly, in order to trisect an angle, and it looks like we're trying to trisect angle ADE here, you need 2 rays. In this case, rays DB and DC appear to be trisecting angle ADE. All right, and so here are some corresponding descriptions of what's going on associated with these figures that are 2 examples of a trisection. Okay, great. Moving on to straight angle. This is a particular type of angle that doesn't seem like it's an angle at all. In fact, it looks like a line. You could categorize this figure here as line AC if you wanted to, or you could call it line AB or line BC. You just need 2 points in order to name a line using points. And just notice that if I was to categorize this line as a straight angle, which all lines can be categorized as a straight angle, you must simply have at least 1 point on it that's acting as the vertex. So in this case, I am in the figure seeing straight angle ABC. That also could be otherwise categorized as line AB or other such names that are appropriate. Okay, and straight angles measure 180 degrees. So that's why I have this labeled here. Okay, now right angles, on the other hand, are exactly half that, or your 90-degree angles. So here is angle F that is acting as a 90-degree angle, and 90-degree angles or right angles are so common in geometry that we have our own special symbol that we put inside the interior of right angles, and it's just a box. So anytime you see a box inside the interior of an angle, you get to right away assume that it's a right angle. Okay? Intersect. So we probably have a very common knowledge understanding of what this word means. Technically, it's when 2 lines or line segments cross one another, and there is always a point of intersection, which I've labeled here as P. So if I was to describe this figure in great detail, I would say that there is a point of intersection P between intersecting lines L and M. There's a special type of intersection and that is called perpendicular, and that's when 2 lines intersect such that a right angle is formed. In fact, all of the angles formed are right angles when 2 lines are perpendicular to one another. So in this case, with this figure, we would say lines M and N are perpendicular, since at least 1, but technically all 4 angles formed are right angles. Okay. Great. Oh, and this is where I will remind myself that we have a construction demonstration. I'm actually going to do that in a separate video. So look for that same video in this week 3, day 6 material. Okay, so let's move on from there. So that concludes section 3.2 material, and now we're technically moving on to section 3.3. And you'll notice that there's actually no place on your lecture notes to write what I'm about to just go over with you. It's more of a conceptual thing that I just want to make sure that I say out loud so everyone can understand this. As far as moving forward in this discipline, we're going to think about our mathematical systems here. And so the first thing that I want to describe as far as the mathematical systems that we're going to be undertaking in this course are the collection of vocabulary. So we've already defined quite a few terms in this first section in chapter 3 that we've covered, 3.2. But there's definitely a lot of undefined terms that are coming your way. Collectively, they make up the vocabulary, and as we move forward, every day that you watch lecture videos and become engaged in this material and you learn about these concepts, you are collecting more and more vocabulary. And so I like to think of this visually as like your basket of terms that you have at your disposal. At the moment, your basket is not super full, but by the end of the semester, it's going to be just overflowing with terminology. Anyway, so definitely there's going to be lots of things that are just defined for you, and it's going to be your job to know the definitions of those words. Not to be regurgitated on exams or anything like that. That's not something that I examine you on, like just say, oh, what is the definition of a point or anything like that. But you need to know what those words mean. Every word that's defined in this course, it's your responsibility to know their definition in order to use the terminology correctly and to understand what is meant when certain questions are being asked of you. Separate from that, but still very much within the realm of mathematical systems here, are axioms and postulates, which are items that we get to just more or less take for granted. They're given to us. They seem very much like theorems, but they're not things that we need to prove. We get to just use them right away as soon as they are presented to us. Whereas theorems, another type of principle, is those are things that we will need to prove in this course, and we're going to prove them by writing proofs. I know that was a terribly redundant thing to say, but that'll be the mechanism by which we are able to use theorems later on to write more complicated proofs. You're always going to be either proving theorems yourself, we will prove them in lecture videos together, or the book will prove them, or we will just move on from the section in which it was introduced, in which case it'll just be assumed that it's proven and we can use it to write future or to justify certain steps in future proofs. If you are hearing what I'm saying and you're like, I have no idea what you mean by that, using theorems to prove more theorems, do not worry. I will definitely make it abundantly clear once we start writing our own proofs what I mean by that. So now we're going to just take a little bit of a systematic look at characteristics of a good definition. So among those first collection of things in the mathematical systems that were just discussed, terminology. So a good definition does these four things. It names the term being defined, like you can't define something without the term that's being defined. It places the term in a set or category, and that gives it context, and that's very important because sometimes the same term will be used in a different context and it'll have a totally different definition. Next, it distinguishes the defined term from other terms in a concise way. So there won't be a confusion of what, if it's a good definition, that it's, trying to define some other term. And then also, and this one is very much akin and leading back to something that we learned in Chapter 2, which is good definitions are reversible, which means you should be able to use the word if and only if in the wording of the definition, and that should work. So it's therefore biconditional. That's a key word that was introduced in Section 2, or Chapter 2 rather. Chapter 2, Section 3, if I'm not mistaken, is when we talked about biconditionals for the first time. Okay, so here is an example definition, and it's boxed in your lecture notes here. Congruent angles are angles that have the same measure. Does this definition have the four characteristics of a good definition? I would say that it does. So it defines the term congruent angles. So yes, it uses the term, check. It puts it in a set or category. Sure, we're talking about angles, right? And so we're not, and so we get from that, just the use of the word angles, what the context is. And also we know that we're not talking about other geometric visualizations, right? We're not talking about line segments or rays or anything like that. We're talking about angles specifically. So we distinguish it from other terms, and it is indeed reversible. So it's true to say that congruent angles are angles that have the same measure. It's just so you know, it's also true to say that angles that have the same measure are congruent. Okay? Works either way. So now we are ready, I think, to introduce several postulates. We go through, looks like 7 postulates. We're going to define another new term, and we're going to, by the end of this lecture video, introduce our very first theorem. Monumentous day for us here. Now, postulates are things that we get to just assume are true. We don't need to prove them. And you will find that a lot of the wordings of these postulates will just seem like such forehead slapper, common sense statements that you'll be like, really? Did we really need to say that out loud? Yes, we did. And we need to just be okay with that and not be super annoyed by the obvious nature of some of these postulates, hopefully, and just understand that this makes it so that we're all coming at this material from the same foundation. Okay, here is postulate 1. It states through 2 distinct points there is exactly 1 line. So this postulate 1 is written on your lecture notes, but I did provide a space for you to add maybe your own 2 points and put them anywhere on the page under postulate 1, but maybe, on top, before you get to postulate 2. Right, in an appropriate area, put the points down on your page. Label them A and B if you want. You can give them any uppercase letter that you want to if you want to make yours different. Now, ideally with a straight edge, go ahead and draw a line that connects the 2 points. Is that the only line that you could possibly draw? Well, within reason. Maybe the line that you drew might have been extended further or not as far in the physical representation of the line, but remember, lines are defined as straight trajectories that are infinite. So the idea is supposed to be that this line technically goes on beyond the area point in which it points. So, okay, cool. So there's only 1 line that's going to be able to go through any 2 points that you put down on your page. That's postulate 1. Another way of before we move on, another way of wording postulate 1 that you will find that I tend to use later on when it's relevant to use it for the purposes of writing a proof is 2 points determine a line. So anytime you have 2 points in a figure, you can draw a line connecting them. It's going to be very powerful for us later on. Okay. Postulate 2, aka the ruler postulate. Now, some of these postulates have specific names to them. Postulate 2 is a case in point. It's also called the ruler postulate, but not all postulates have names to them, in which case we want to just get to know these postulates and theorems, for that matter, by their content. The last thing that I want to do is be bogged down with trying to memorize these postulates by their numbers or by their or the theorems by their numbers, because the theorems are going to be labeled according to what section they came out of and in what order they were presented within that section. So, for instance, the theorem that's introduced to us today is going to be theorem 3.3.1. But I don't want us to get to know that theorem that way. I'll let you know what I mean once we actually introduce that theorem at the end of this lecture. So, what does the ruler postulate say? It says the measure of any line segment is a unique positive number. Think back to our example of a measuring line segment RS in the previous section, also in this lecture video though, just earlier in the video, where we said, let me go back. This line segment RS had a unique positive number, 8.5 centimeters as its measurement. So it's not any other measurement. It only has one possible measurement. It could have a different unit to the measurement, like if we had measured in inches. That's not saying that we have a different distance, though. See, the distance is supposed to be a unique positive number. That's what this postulate is going at. Okay, here's another postulate that has a name. It's called the segment addition postulate, aka it's the third postulate being introduced, so it also was called postulate 3, but we want to get to know the content of it, which is to say, if X is a point on line segment AB and AXB, this notation right here, this AXB with the hyphens, is just stating that A comes first, X is in the middle, and B comes last, reading it from left to right as far as the placement of the points on the line segment are concerned. Then the measure of line segment AX plus the measure of line segment XB equals the measure of line segment AB. So think about this. Yeah, the previous example that we had in section 3.2, certainly we found that to be the case because AX has a measurement of 3.5 centimeters, XB has a measurement of 5 centimeters. You add them up and you get the collective measure of line segment AB, which was 8.5 centimeters. Okay, anyway, so you can add all of that to there if you want to, as far as wording is concerned. All right, we're on postulate 3, so if you're following along with lecture notes, we're turning the page there. It says, if two lines intersect, then they intersect at a point. Yep, go ahead and draw yourself two lines. You could follow my example and make your lines look kind of like mine and label them lines L and M. You could give them different names if you want to. Just remember that lines have lowercase letter names to them when in the absence of having points on them. But the place in which they intersect is a point, and I'm going to go ahead and explicitly label it with a dot and call it point P. And there you go. So they intersect at a point is the point of postulate 4. And there you have it. All right, now we're going to throw in a definition. Parallel lines are lines that lie in the same plane but do not intersect. So I'm not bothering with putting them in a plane here, but just pretend the surface of the paper or the surface of your screen, if that's how you're seeing this alone, is the plane. And then lines M and M are in the same plane and they will never ever intersect. It's like tragic love story in the mathematics community. Parallel lines. So sad they'll never intersect. Okay. Anyway, postulate 5 states, through 3 non-collinear points, there is exactly one plane. Okay, how do we represent 3 non-collinear points? Well, just put 3 points anywhere on the page there. All right, and then say to yourself, all right, well, they're on the page, which is actually a pretty good physical representation of a plane itself. Or you could add yourself a plane like I've done here in gray, and I've named it plane P. So planes have fancy uppercase letter names to them oftentimes. Not something that we have really introduced in this course formally, mostly because it's called plane geometry. Everything is that we care about in this course happens in 2 dimensions or on planes. So thinking about planes in 3-dimensional space is not something that we need to be terribly concerned with in this course. Anyway, here is a plane P that you see in gray. Think of it as a sheet of paper, so to speak. These 3 non-collinear points, these three points do not lie on a single line, right? There is exactly one plane in which they could lie, and that's the sheet of paper that is represented here in this gray plane P. Okay, that's all. Postulate 6 states that if 2 distinct planes intersect, then their intersection is a line. So let's imagine 2 planes intersecting, planes alpha and beta. Okay, so yeah, sorry, I think I said uppercase letters. They just have to be fancy looking letters. There's actually not a hard and fast rule for the naming of planes. And here, Greek letters are often used. So here's plane alpha, plane beta is like this darker gray, like horizontal looking one. And they're intersecting at line AB, okay? That's the infinitely many points of intersection forming that line. Postulate 7, moving right along, says given 2 distinct points in a plane, the line containing these points also lies in the plane. Okay, so give yourself a plane F and put 2 points A and B on it, and then try your best to draw the line that intersects those points. Now the line is going to go on forever, so technically does the plane. That's a whole nother concept for you there, but very much related. And so yeah, the only way that you're going to be able to draw that line through those points is to have it also lie on the plane in which the points lie as well. That's the point of postulate 7. All right, here we go. And now we are ready to wrap things up with our very first theorem ever, one of very many that will be presented in this course. This is like the beginning of an age here, in which we are being proposed to believe that the midpoint of a line segment is unique. So as a visual, we can rely back on our RY, YS line segments and note how the position of point Y was special in that it was being categorized as, a midpoint, because the measurement on either side of it in terms of the endpoints of the line segment were equal to each other. So this theorem is just expanding on that definition to say that the midpoint is unique. There can be no other midpoint on a line segment of a fixed length. So if you hold on, let's just see. Sorry, I paused for a second there. I was just getting my thoughts together. Yep, and we are therefore proving this theorem by example, and just saying that, you know, anytime you're going to have a fixed length, you're going to have some only one unique midpoint that's going to cut that line segment in half. Okay, and there's a little bit more in the book about that as well. Definitely skim through your book in order to make sure that you're getting all of the information that you need here in order to tackle your homework. And so now here are the two sections, selected problems that I recommend that you tackle. Notice that there's an even problem here and there, which, you know, won't be necessarily in the back of the book, but we can discuss them in class, or if there are any problems whose solutions are not in the back of the book, which could happen, and you want to confirm or deny that you have, done that problem's exercise correctly, let's talk about it in class. It's precisely what class time is for, and that's all I've got for you today. So I will see you soon in class. Look very much forward to that. Take it easy, guys.